right. AC review. AC stands for
Alternating current.
alternating current. Zero volts. It's important to understand that this is AC, but this is DC.
Mm-hmm.
Right? Because all of the current's moving in the same direction. It's all moving, less of it here, more of it there, but here we've got current moving in opposite directions. Polarity reverses, you get current flowing in the opposite direction, right?
Mm-hmm.
Okay. So, if I'm moving in one direction versus moving in the other direction, let me ask you a stupid question. If you drive your car backwards, do you make gasoline?
Do you make gasoline?
Yeah, does your car manufacture gasoline when you drive backwards?
I don't know.
Or does it consume gasoline to drive backwards?
It's consumed.
Of course, it consumes gasoline no matter what direction you're moving,
Mm-hmm.
right? So, just because the voltage is negative, does that mean that there's energy being put back into the system? Or does it mean that we're continuing to take energy out of the system, we're just going backwards? It's the same question, right? So when we talk about the energy, energy doesn't care about polarity. It's the same amount of energy to get from A to B as it is from B to A, which means that when we look at energy, we're really looking at this. Right? More energy, less energy. More energy, less energy, but in the opposite direction. So independent of direction, the energy that we're using looks like this. Okay? And you can see that it varies over time. Correct? If I were to take an imaginary line and draw it right about here, then these little pieces on the top will fit into these gaps on the bottom exactly, and that will give us an estimate of the overall constant energy. Okay? In other words, mimic DC by averaging an AC signal.
Okay.
So, if this is +3 and this is -3, how do I get that -3 to become a +3? How do I flip that up?
Frequency.
Nope, has nothing to do, it's all polarity based, right?
Add a. You just add it in.
What we do is this. -3 times -3 is equal to what?
Nine.
-9.
How much?
9.
9. +9. The square root of +9 is equal to 3. So if I square a negative number and then take its square root, it eliminates the negative sign. That's all it does. Right? And then, one more thing we'll do, after we flip this up like this, we'll take our average. And the average for this type of arrangement happens at 0.707 or 70.7% of the maximum voltage. So 70.7 of 3 is about 2.1 volts. Okay, so we took that -3 and we did what with it? We squared it. We took the root of it. And then we took the average or the mean. Okay, in electronics we call that RMS for root, mean, square. Okay, the root and the square are doing this, and then when we take the average, filling in the gaps with the overages, that's where we're taking our mean being another word for average, basically. RMS gives us the average amount of energy over time. And it's 70% of the peak voltage. Okay, so that RMS is more than just a bunch of letters crammed together. It actually does mean something. 2/3 of it involve getting rid of a negative sign by squaring and then taking the root. Okay, so we need to be at that point because we need to understand that when we look at what's coming out of the wall, it's 120 volts RMS. So that means it's more like 180 volts peak. It's getting close. So we have to be aware of that when we pick components, because the components have to be able to deal with the peak voltage. All right. I think we showed last week, I think we got this out, didn't we? The slinky?
No.
We didn't?
Can't do that.
So then somebody needs to come up here.
Thank you.
So if you hold on to the slinky and take it over there, try not to stretch it too much. Hold up close to the wall. You hold it still and I'll stretch it.
Okay.
All right, if you look at this from the side, does it look like a sine wave?
Yes.
but yet it's actually a circle, right? So if I go, say, hold that still, if I go from here or to there, right? That's one complete circle, right? 360 degrees. I don't do well right-handed. Okay. So whenever we look in the, let's have a seat. So whenever we look at a sine wave, we're actually looking at a corkscrew. We're just looking at it in 2 dimensions. Okay? Sine waves are circular because that's typically the way we create electricity. How do we create electricity? Windmills go in a circle. They create AC. Turbines at the dam. Water makes turbines rotate in a circle. You go to a nuclear power plant, the nuclear power is turned into steam, which turns the turbines and generates AC. So AC is generated by moving things in a circle. It's how we generally make most of our energy. If we want to make DC, we can do it with solar, or we can use batteries, or we can convert AC into DC, and that's what we're going to talk about next. Converting AC to DC. And in order to do that, we need to introduce a new player on the field.
The diode.
Right. Okay, I don't know which side of the fence you guys are on. But whichever one, whichever way your juice flows, the diode will only allow it to flow in one direction. Other than the one on the board, I can think of 16 diodes that are in this room right now. There are 16 diodes in this room right now, and if one person leaves, there'll only be 12. If somebody comes in, there'll be 20. So what the hell is the old man talking about?
Hey, what the hell is old man talking about?
Your heart has valves.
Oh.
Your valves only allow blood to flow in one direction.
Okay.
That's what diodes do. Because if you think about your heart is just a muscle that squeezes. It's kind of like a bulb. If you squeeze it and then release it, it's going to suck the water right back in again, right?
Right.
So you need to have something that lets the water or blood out, but doesn't let it come back in when the pump relaxes. Okay, you also see these on sump pumps in your basement. When you pump air out or water out, you want to make sure the water doesn't just come right back in. Okay, so we see diodes all the time in the real world, but in electronics, they're little tiny things that restrict the flow of current to one direction. So, you guys are probably more into the electron flow realm, is that correct?
That's, yes.
You guys, your current goes from minus to plus.
Correct.
So we'll work on that then.
Does the Tron class do DC?
No, we do plus to minus.
Okay.
So I have to switch every time I teach a different class.
Okay.
Yeah.
Okay.
All right, let's establish some basic ideas about diodes. In a simple circuit, current is going to flow this way. And as such, is the diode on or is it off? Is it conducting or is it not? Remember, it determined which way does it let current go. And I guess the way for you guys to look at it is you've got an arrow and a brick wall here, so current can't go in that direction.
Mm-hmm.
I teach my other class that has an arrow, so current does flow in that direction. But yours, you look at it as an arrow going up against a wall, current cannot flow in that direction.
Okay.
So our current's flowing this way, so the diode is on.
That's a good way to look at that.
Yeah,
The only thing that's confusing to me is the wall's there, so it will be like it's, but instead you have to go through the arrow first, so that's kind of like going through the door, right?
Yeah.
Right.
So I don't know how you justify it or how you remember it.
Because like, well, obviously this is, well, when you're going here, it looks like that would be the on because of the arrow going in, but it's not. Obviously, this the wall would kind of.
Yeah, anything going in this direction hits the wall, I guess.
Yeah.
You know, when they developed the schematic, I don't think they understood the difference between electron current and conventional current, because conventional current is called conventional because it was first,
Right.
right? You look at a water tower and you
Right.
assume that everything flows from higher pressure to lower pressure.
Well,
But remember, every time water leaves that tower, air has to go in to replace it.
mhm.
And that's, that's where we are. We went through that last week. But nonetheless, the diode is on. Now, here's something I need to tell you. Diodes got really smart at some point. They decided, you know what? We're not doing this for free. So the diode actually charges a tax to do its job. That's one way to look at it. It uses up the first 0.7 of a volt. So it's going to steal 0.7 of a volt from your energy, right? Traffic cops don't work for free. All right, so IT is equal to how much? How much of the current?
We've got, so
12 over.
divided by the 1 kilo.
What's that? What did you say?
12 divided by the 1 kilogram.
Kirchhoff is spinning in his grave right now
I,
on a spit going at least 100 times around a second.
yeah,
I is equal to V over R every day of the week, right? So Ohm isn't pissed off, but Kirchhoff not happy. No, not happy with your answer. Somebody else want to give a better answer than 12 divided by 1K?
Do we have to subtract the 0.7 from 12? First?
You're going to have to ask Mr. Kirchhoff that question.
oh yeah, hold on.
Mr.
man.
Kirchhoff.
Mr. Kirchhoff says that the sum of all the voltages around a circuit has to add up to the source. So you tell me.
Kirchhoff is, okay, so we're not doing ohms. Kirchhoff is this, voltage, the resistor.
Kirchhoff is the accounting for the energy. Right? You should have had this in first quarter. 12 volts has to be the sum of this and this. So if you've used up 7/10 of a volt, that means you must have 11.3 volts across the resistor because they add up to 12. Right? Remember? Everything has to add up. So my current then is not going to be 12 milliamps, it's going to be 11.3 milliamps. Right?
Yes.
Here is an even tougher question. What is the resistance of the diode?
On 7 volts,
Resistance is not expressed in voltage, sir.
0.7 ohm,
Tell me how you came up with it.
because a resistor slows down the current, and I saw the diode as a resistor because
It does, but it's not, I need to know how you calculate it. If you're going to tell me it's 0.7 ohms, I want to know how you got it. Maybe you just saw the 0.7 volts and assumed it would be the same number.
yes.
Okay, well, that's not correct. Anybody else? The information you need to determine it is right there in front of you. So I'm not being a dick. I just want to see if you can find it.
The voltage divided by the total current, or 0.7 volts divided by total.
R is equal to V over I. The voltage across the diode is 0.7 volts, and the current is 0.0113 amps, or 11.3 milliamps. And that is the correct answer. Thank you. But I don't have a calculator, so somebody else is going to have to. $70 ohms ish, 65. I'll go with 65 as my estimate.
I got 62.
We'll call that. Should be about close to 62 ohms. If I change the value of this resistor, will that change the resistance of the diode? And the answer is yes, because the current will change. 0.7 of a volt will not change, but if the total circuit current changes, then the resistance of the diode changes. So we can say that the resistance of that diode is dynamic because it depends on the circuit it's in. It's not a resistor. It doesn't have a value of resistance. It depends on the circuit. We change the current. This stays the same, the current changes, that has to change. So we generally don't talk a lot about diode resistance. The reason I asked the question was to try and lubricate the joints that are in your brains to get you thinking about Ohm's law and Kirchhoff's law. Because those, instead of being the problems, those are now the answers to the problems. So now you have to use those laws to wade your way through solving these problems. They become now the tools. Does that make sense? You look confused about that.
I am very confused. No, not confused about using the tools. It's like, once again, I'm back at the IT here. And if I'm not using Ohm's law, I'm using Kirchhoff law to solve for IT. Now I've got to go back. So
Well, you're using Kirchhoff's law to get the voltage across the resistor.
Okay.
And then you're using Ohm's law to get IT.
IT, right.
Because you have 11.3 volts over 1K. And that gives you 11.3 milliamps.
Yeah, because I stole the volts from the, right.
Because we stole 7/10 of the volts from the source here. So everything adds up,
Yeah.
right? That's the important thing. Everything adds up. And what guarantees that is Kirchhoff's laws. So we have to embrace them because they're functionally what tell us that we can balance our budget. Because whatever goes in has to come out. You can't have more voltage here than you have there. It's got to be the same. Okay, any questions on what we did here? I'd like to erase it if you're ready. You waiting? You still need it?
No, I'm good.
You good?
Go for it.
All right, now let's take our AC waveform and shove it through a diode. Zero volts? Yes? No? Yes? No? Yes? No? Reverse polarity? Only 1/2 of that waveform is going to go through the diode. Because the rest of the time the polarity is reversed and current's trying to flow in the other direction. Which means that what we'll get out of here is that. And it will never go below that 7/10 of a volt.
So that's always the minimum for diode?
Yeah, for silicon that we're talking about right now. There's another material that diodes are made of called germanium. Silicon is a lot easier to find than germanium is. So germanium actually gives you a lower voltage of 0.3 to get through that one. Charges much less tax, but they're very rare. We don't use them very often. The only time we use germanium is when we're trying to receive really weak radio signal, because we use diodes in radio reception. So you're going to get a waveform that looks like this, like Hump Day. Rectifier. Today's word of the day. What does it mean? Rectify.
To make right, to solve, to.
Correct.
In a sense,
Yeah.
but when we talk about a rectangle,
Okay.
all right, rectangles, RECT, Rectify. I need to rectify that situation.
So we want rectangles.
What it really means is straighten out. So if I'm rectifying something, literally the translation for rectify is to make it into a straight line.
Okay.
Or when we use it colloquially, I need to straighten out that situation, or I need to rectify that situation.
Correct.
Means straighten out. And for us, straighten out means AC to DC. Because AC looks like this, and DC looks like that.
Mm-hmm.
And is this DC?
That
Yes.
is not the, well, no, it's got the lines in between.
Doesn't matter. Does it ever go across the 0 volt
No,
line?
it's DC.
So it's DC. It's pulsating DC, but it's DC nevertheless. That's not what my dad told me I'd have when he said DC. When my dad talked about DC, he always said it was going to look like this. Straight line. How is that a straight line? It ain't. So we need something else. Let's put something out here. Our load. What the hell is a load? What is it? What does that word mean? We use it all the time, right? What does it mean?
The amount of power or the amount of,
Why does the circuit exist? To deliver power to something. Whatever that is the load. Might be a charging cell phone, might be a fan. Whatever it is going to have some kind of resistance or reluctance to current. So this is what you're powering, right? So what we're going to do is we're going to put one of these in here. Okay? Now, when we go back to our Humpty Hump stuff, what we're going to see is capacitor charges on the positive end. When the input signal goes away, the diode turns off. Capacitor has no choice but to discharge through the resistor or through the load, maintaining the voltage across the load by doing so. It goes down, it gets lower, the capacitor discharges, and then it gets another boost when the next pulse comes in or the next period starts. Charges, discharges, charges, discharges. And by doing that, maintains a fairly consistent DC value. Okay, so now we are getting to the point where we can take an AC signal bring it into a diode, turn it into pulsating DC, put it through a capacitor, and turn it into very close to DC. And then that's what goes to our load. This is what we call a half-wave rectifier because it uses half of the waveform. The other half is just blown off. It never makes it through. It's kind of a waste. Things to look forward to. Can we do a better job? Is there a way that we can do a better job so that we won't have as much of this variation? Is there a way that we can use both halves of the energy that's being delivered to us? We're getting a box of energy and we're only opening the box and using half of it. We're throwing the rest of it away. And the answer to those questions is, of course, yes, or there'd be no reason to continue with this discussion. So we have made a half-wave rectifier here. That's what we have built. Next time we meet, we will turn that into a half-wave power supply. And then, after we do that, we'll start talking about ways to get full-wave rectification where we're using both halves of our waveform. We'll need 2 or more diodes to do that. Okay? Anybody have any questions on what we did today? What did we do today? We reviewed AC. We talked about RMS. Hopefully you have a better understanding of what RMS actually means. And then we got into diodes. We established the basic functionality of a diode, determined its resistance and current and voltage in a circuit, and then used that diode to convert AC to DC. So I'd say we got a lot done today.
Yes, sir.
Maybe not a whole lot of math, but you know, that's the way I roll.
Okay.
All right, any questions on anything? Stay tuned, we got a new toy today.
Is the forward voltage at 27 volts?
Yes,
Okay.
yep, that would be the forward voltage.
Forward voltage.
Forward.
We got a borescope. You know what a borescope is?
A borescope? I do not. Does it dig into something?
No, it's actually pretty cool. It, you know, I'm going to turn the recorder off so that nobody else hears this.